Okay, welcome back everyone. Please join me in welcoming our last speaker of the session today. Our last speaker is Philipp Krähenbühl, and he's an assistant professor in the Department of Computer Science at the University of Texas, Austin. He received his PhD in computer science from Stanford University and then spent 2 years as a postdoc at UC Berkeley. His research interests lie in computer vision, machine learning, and computer graphics. He is particularly interested in deep learning as well as image segmentation and understanding. We are very much looking forward to his talk. Philipp, the stage is yours.
Great. Thank you for having me. And sorry I couldn't be there in person. I would have loved to come visit Tel Aviv, but sort of life had other plans and I had to stay here. So one thing I want to sort of mention before I get started, I'm currently sort of splitting my time between UT Austin and Apple, and I want to make sure that this work I'm talking about here has nothing to do with Apple. It's all UT Austin's work. All right. And so the other thing I want to mention is if you have any questions throughout the talk, if there is a microphone, just walk up and ask. I don't mind being interrupted if you're in the chat. If there's questions in the chat, I'll try to monitor that as well. Okay. All right. So I would say we live in a really exciting time right now because about every 10 or so years in computer vision, there is sort of a new cool idea coming along. And in the early 2000s, this new cool idea was data sets, that we sort of started to standardize computer vision tasks in large parts initially just recognition tasks around sort of standard benchmarks and data sets. Now, there have been benchmarks and data sets earlier than 2000, but in the early 2000s, they really started to see the proliferation of these data sets. And as you probably all know, in the 2010s, deep networks came along, and sort of they really rode on this big wave of data sets and sort of took all the beautiful and creative sort of tasks or solutions that you have for computer vision tasks and sort of shoved them through this monolithic block that is sort of an ImageNet pre-trained CNN, and we saw sort of huge improvements in numbers. And I would argue sort of the cool new idea of our time is actually transformers. And it's not necessarily the attention in transformers, but it's a cross-attention operator. This is something that we haven't had before that allows us to sort of solve many exciting and cool new problems in cool new ways. And I'm going to sort of show you a little bit on how I think transformers are going to change computer vision in the next few years to come. But before that, let's look at how we did computer vision before we had transformers. So the way we did computer vision before we had transformers was we essentially took an image, we shoved that image through some CNN, and out came some sort of feature map that we then either ran some classifier on. We extracted boxes from these feature maps to do detection. We even densely classified these feature maps to do semantic segmentation or monocular depth estimation, you name it. Now, one thing that all of these sort of networks had in common is that we had to think really hard on how to take an image, stuff it through one of these CNNs, and then sort of take the output of the CNN and then do something with it and solve the task we want with it. Now, initially, transformers actually didn't change that paradigm very much. So we still had sort of an image. Now we just chop it up into multiple small little patches. Now we stuff these through now a transformer. And out come sort of little transformed patches. Still sort of maintained all the nice properties of CNNs. If we sort of put n patches in, we get n sort of outputs from this transformer. There is something special we could do. We could add a classification token here and transform this as well. This is sort of a special way to do image classification, but it turns out it's actually not really needed to do well in image classification. So that this classification token is something that came from language, but in vision we didn't really need it. Now, the one thing that does change with transformers is there's a second operation we can do, and that is cross-attention. And this is best illustrated in a very beautiful object detection paper called Debtor, where we're taking an image as an input. We'll feed it through some backbone. That can be a convolutional backbone, or it can be a transformer backbone. We get some representation out of this. It's still sort of roughly the same size of the image. But now we're going to use cross-attention to do something slightly different from what people have done before. We're going to start out with some very abstract tokens. You can think of these as sort of abstract feature vectors. And now we'll use a cross-attention operator. On one side of this cross-attention, we feed in the entire representation that we extracted from our image. On the other side, we'll feed in these queries or these tokens. And now what cross-attention allows you to do is it allows you for each of these queries, you can look at the entire image to extract an output feature. Now, this is an operator that we haven't actually seen in vision. Well, the closest we have gotten in vision to this was sort of bilinear kernels back in 2005. But this is an operator that was actually not really prominent or centered, featured like front and center in computer vision. An operator that can take sort of one set of values and transform it using another set of values. Now, what Debtor does with this is it takes these queries and it transforms them into bounding boxes in the image. And so this is a way to take sort of an arbitrary number of very abstract queries and produce a number of corresponding bounding boxes as an input. And this is just one example of sort of how to set up a vision problem in a very, very different way. Because before, the way we solved object detection was we sort of slided a bounding box over an image and wastefully asked the question, is there an object there, is there an object there, is there an object there? Now, all of a sudden, we can just have this one operator that takes abstract queries and transforms them into output boxes. The nice thing is this is fully differentiable, and you can learn it in an end-to-end manner. Right? Now, what I'll show you in this talk is that detection is only one instance in which sort of this cross-attention operator allows you to just completely differently think about the way you set up a problem. And I'll first show you how we can think about sort of cross-view geometric reasoning as just sort of one or a few layers of cross-attention. And then I'll also show you how we can do global tracking. So tracking not just from one frame to the next, but tracking over an entire video clip as sort of a bunch of sort of layers of a transformer. All right. And so let's get started. So we'll start with the multi-view recognition. At the end, I'll also sort of highlight a little bit what we're gonna present here at ECCV, just as a little bit of a teaser. But let's start with multi-view recognition first and sort of set up the problem. Now, multi-view recognition, the goal is to sort of take a bunch of views captured from a vehicle, from cameras that are mounted on a vehicle, and each of these views sort of overlaps a little bit, not too much, but it overlaps a little bit on the side. And now our goal is to take these views, these slightly overlapping views, and get sort of a 360-degree sort of 3D view of the scene around us. And now in the problem that we're looking at here is this 3D view is just going to be sort of a map down here. And we'll mainly focus on vehicles and on the road here. So we're going to infer a map of the surrounding, and we're going to look at where all the vehicles are and where the road is. Now, this problem requires a lot of 3D understanding of the surrounding. We need to build up this 3D understanding from multiple views, and then take these 2D views and project them into a 3D map. It requires us also to sort of anything that overlaps sort of between views, like these two views here, it requires us to come up with a consistent answer for this. So we'll have image features for sort of this part and this part, and the network is required to come up with just a single consistent answer for what these what's in the scene at this point. We'll need to fuse information from multiple views, and we'll also need to get some sort of depth estimate to be able to project information from sort of these 2D views into 3D. All right. Now, the first option, if we want to tackle this problem, could be, well, we have a little bit of overlap. So if we want to infer 3D, why don't we just use sort of the overlapping regions between these cameras and just run some sort of stereo algorithm. Now, if we look at sort of the setup of the vehicle, in most data sets, this looks something like this. You have a front-facing camera, you have a back-facing camera, and then you have sort of a bunch of side-facing cameras. And each of these cameras overlaps in some region. Now you could place more cameras and have a higher overlap, but we could just say, okay, let's look at this overlapping region and run stereo on it. Now the main reason why this is actually a pretty hard problem is that the cameras are not perfectly aligned. You could mount twice as many cameras and then get stereo for free. That just would be a bit more costly. But in the current setup, these cameras are not very well aligned. They're not parallel to one another. And so the stereo problem is actually relatively hard. And so in prior work, nobody actually chose to ever try to estimate stereo depth directly from these views. What people do most of the time is they actually go a slightly different route. They do monocular depth estimation. And that monocular depth estimation now allows you to align sort of the view from one camera to the scene itself. And so with monocular depth estimation, the way this alignment works is I'm going to draw the side view of the car here. So you have some camera on top of the car here. You're now going to say, you're going to have the image plane here. And what monocular depth estimation just says, it tells you how long the ray is that is cast from the camera into the scene. And now, if you know how long this ray here is, you know where it projects into the scene. And there's two really amazing papers on this. There's Lift, Splat, Shoot, there's Fire, there's a couple of more in this general realm. But sort of the idea of just going from monocular depth to 3D sort of comes from either Lift, Splat, Shoot or Fire or both. And this is a really nice idea. It has many appealing properties. You can feed all of these images through a CNN, you can get a monocular depth estimate, and all of a sudden you get a 3D understanding of the scene. Now, the issue, there's sort of two issues with this, which is, number one, you need to rely on a very, very good monocular depth estimate. So in order to project things properly from 2D into 3D, you need a good monodepth estimator. Now for driving, this somewhat exists for simple things that you've seen in a data set before. So if you have sort of road patterns, their monocular depth is relatively easy, maybe even for cars that have a common shape. It might not be very accurate if you get to see sort of some vehicles or patterns that are out of distribution. Now, the other issue is that monodepth is not always consistent. So what do you do if you have two regions in two images that project sort of onto the same part of the scene, but you get different features? Right? So you need to come up with a way to resolve this. And it also ignores any sort of stereo cues you could get from the scene. Now there's a third way of thinking about this problem, which is instead of trying to estimate the depth from the camera to each point in the scene, we could instead try to infer the height above ground on the map. And I'm going to draw the same sort of car picture again here. We're going to again have the camera plane here. And I'm going to draw the ground plane here. Now, if I knew for every point in the scene, if I knew how high it is above ground, this would give me enough information to project it back into the image plane, right? So think of sort of the monocular depth estimate as trying to project things from the image plane out into the real world. What the height above ground estimate does is it projects things back from the world back into each of the image views. And this is exactly where we can model things with sort of very nice cross-attention and with a transformer. And so what we're going to do here is we're going to build up a representation for height above ground. We're going to build up a representation in map view for what we think the height above the ground is. And then we're going to use a transformer to do all the geometric reasoning to project points from the map back into each of the images here. Right? I'm going to show you over the next few slides how we built this up. All right. So let's get started. So the way we're going to build up this transformer that builds up the height above ground is we're going to have some sort of initial representation of our map around the vehicle. We're going to extract features from each of the images. It's just some sort of feature map that we get from a CNN. And now we're going to build a cross-attention operator that takes the map representation as queries. The keys and values come from all of the images, and we'll get an updated map representation as an output. So we're going to transform the estimate of our sort of surrounding of the map that surrounds us, and we're going to use the image features to transform that estimate. And we're going to repeat that. We're going to go and repeat this a bunch of times. And over time, we'll build a more accurate model for what the surrounding, what sort of the world around us looks like. Initially, this very initial estimate here, this is just going to be some sort of prior, sort of the average world around us is usually sort of flat roads and we don't quite know anything about it. Now, after the first iteration, we'll have some idea what the geometry looks like in the world around us. And more importantly, the transformer can also reason about what the appearance looks like in the world around us. So it doesn't just need to solely rely on geometric features. It can also rely on appearance features to build up a representation of the world surrounding us. And then we'll go through it again and refine this representation over and over again. Right? And so in practice, this looks more or less like this. We start with the map embedding. We have positional embeddings for all of the points in the image. And these positional embeddings here, they actually are produced from the camera calibration itself. So each camera has some sort of calibration in each of the scenes, and we'll use sort of the center of the camera, and for each pixel we'll use sort of the center of the image plane of the location of the image plane of the pixel in the image plane in 3D. We'll use that as a feature for the transformer to learn geometry. And then we'll build up this map embedding and transform things sort of to build up a more accurate map embedding. And this will really include both geometric features and color features. And then in the end, we just have a simple decoder, a bunch of convolutional layers to produce the map we want. And that's pretty much it. It's super simple. You don't need to know anything about geometry. You just have a bunch of transformer layers, and out comes sort of a nice 3D geometric reasoning. Now we trained this on the new scenes benchmark for both vehicles and drivable area. And in both, we're sort of at the state of the art, which you can see here. But we're also much, much faster than most of the prior work. And we're faster just because all we do is we have sort of a transformer layer that takes an embedding that's specific to sort of the intrinsic and extrinsic calibration of the camera, and there's nothing else. We don't need to do monodepth. We don't need to think about projection into the scene. All we do is we just run a transform. Here's the result for drivable area, and again, it works generally quite well. All right. And here's some result videos. What you can see here, this is just for drivable area. We're running this and just building up a map as we run this. Here's a slightly different scene. And again, here on the right, you can see how we build up the map. And on the left, you can see the images or the videos that we see as an input. All right. And so the nice thing here is that we could take a fairly complex problem of geometric reasoning in a scene and just replace all of this with just one layer of a transformer. We don't have to know geometry anymore to do this task very well. The only thing we need to know is we need to sort of know that things somewhat depend on camera parameters, and then we just feed in a like gigantic data set and let the transformer and the cross attention in the transformer learn how to map specific points in 3D to other points in each of the 2D views. Now, this is sort of the first part, or the first sort of example on why cross attention is a really cool operator and allows us to do things that we couldn't really do before. The second example we're gonna talk about next is we're gonna look at how can we phrase tracking sort of, and not just sort of local tracking, but global tracking over an entire clip. How can we phrase this instead of an optimization problem as it has been phrased classically? How can we phrase it as just one or two layers of a transformer? And so before we get started, I'll first introduce the problem of tracking. So the problem of sort of tracking is trying to follow individual objects through time. So we want to detect, or we want to figure out where an object is, and we want to be able to tell that over a series of frames, a certain object is the same thing. Right? And so this really involves sort of tracking, it involves detection of objects, and it involves association of these detections. And sort of one of the most prominent approaches in tracking in the deep learning age is tracking by detection, where we really split the problem into two parts. Part number one is we just detect all the objects. So we don't care about association in step number one. We just want to find all the objects in a scene. Step number two, we'll link the objects together. And in quite a few of the works, these are completely different steps. So you run a detector first, and then you run some sort of association between these detections. And this association can have two forms. Either we're going to extract some feature for each of the objects and then do some association in feature space, or we can predict flow or some sort of geometric signal that tells us where we found this object in the previous time. And there's examples on for each of these in the citations group. Now there's another way to think of. There's another way to think of tracking, which is we can try to interleave tracking and detection. So we can try to make tracking and detection closer in sort of one common framework. And that is, we start by detecting objects in the very first frame, and then we're going to take these detections and we're going to initialize as a detector for objects from these previous detections. And so we're going to use the fact that object detection is somewhat robust to sort of snapping to individual objects. And we're going to bootstrap the detector at the next stage from detections of the previous stage. And so the tracking without bells and whistles was sort of the first paper that did this. And then there's a very nice transformer-based tracker that does this using vector queries. All right? And so this is quite neat because it allows you to sort of build tracking by detection sort of almost into just one framework. The main issue is that it's still sort of just frame by frame by frame. So a lot of times there's a lot of sort of heuristic rules involved in how do we design a tracker that allows us to sort of skip a frame for an object if it's not there, and then sort of find it again using the same tracks. And a lot of this is a little bit messy and heuristic. All right. And so this greedy frame-by-frame assignment is really like, it works very well if objects move slowly. It works very well if objects never disappear, if there's never any occlusions. But as soon as we get occlusions, things get a little bit messy. Now, there is an alternative to all of this, which is global tracking. And instead of trying to associate sort of frames just one at a time, we're trying to find globally, we're trying to sort of group together all detections from the same object. We do this globally. This is traditionally done using some sort of optimization. So we'll detect object first, and then we'll run an optimization to globally group all of these objects together. And I'm going to finish this picture here. All right. And so this is sort of the global tracking idea. Now, if I draw this picture like this, where I'm saying I'm going to take these objects, I'm going to group them together in these global tracks, something should look a little bit familiar. So these global tracks, if you just look at it slightly differently, this is exactly the same thing as what we would feed into cross-attention. So you can think of these global tracks as being queries in a tracker. So let's see, these are the different queries. If I told you ahead of time that there's sort of 10 objects in the scene, you could just come up with 10 queries, and you could learn a transformer architecture that looks at all the boxes that were ever detected in all the images. Sorry, this is getting a little bit messy. And then comes out with tracked trajectories or tracked groupings of these boxes. And that's exactly sort of what we did. So we built this transformer. The transformer has queries, and the queries are tracked objects. And then we have a special cross-attention operator that is allowed to cross-attend sort of to all the boxes in one image. Now, usually cross-attention works by sort of taking a softmax over all the inputs, but now here we sort of restrict the softmax to focus at most one object in per image, right? And so the way this works technically is we'll add sort of another token to each of the detections in each of the images, and we'll just say this is the token that says I don't want to track, I don't want to be associated to any of the objects. And then we'll run this cross-attention. We'll do this twice, I think. And that's sufficient to then run this cross-attention a third time to get associations from each of the queries to individual detect boxes. And these sort of associations between queries and boxes is exactly the global tracking. And so now we don't need to optimize anything. We don't need to run any optimization to global tracking. We can learn all of this with just sort of a few layers of a transformer. And this is sort of, what I'm showing you here is sort of more or less the entire architecture, right? So we'll have some self-attention, we have cross-attention, and then in between we have a bunch of MLPs. All right, and we really learn global association of a detector. Now, one of the of a tracker, one of the issues here is that this actually only works if you know how many frames you're gonna track over. So if you're training on frames of on video clips of size 16, so of 16 consecutive frames, this really works well for 16 frames, but it's not going to work well if you go to 32, if you go to 128, or if you go to an arbitrary number. And so a little hack we did to make this sort of global tracker work on an arbitrary number of frames, and also to get sort of an answer in a streaming manner, sort of as you add in more images, you get sort of an updated track. We change this to a streaming version where we use global tracking within n frames. Then we'll switch over to the next frame, and we do a very simple association. So since these global tracks are very long, what we can do is we can just look at overlaps between global tracks of the previous frame and the current frame. And if there is large overlaps, we'll just associate them. Right? So this is the streaming version of this. Now, I'm going to show you some tracking results on the video that I used for a lot of the examples here. And I would like to direct your attention to the dog here. So just look at this dog for a moment. I'm going to show you what frame-by-frame tracking does, and then I'm going to show you what global tracking does. And every single time the box changes colors, that means that we lost track of the object, and we had to we had to figure out where the object is again. All right. So you can see the dog changes colors pretty wildly in the frame-by-frame tracker. Now, if you go to our result, it switched color once, but other than that, the global tracking is super stable. Now, in general, the global tracker actually works better and better the longer you track for. We went up to a size of 32, and so 16 or 32 really works by far the best. If you look at sort of local trackers on exactly the same setup, you can see that they work considerably worse. Now, here are some numbers on the tau data set, and at the time of of publication of this paper, the global tracker here did significantly better than any of the comparable baselines. All right, so here again, sort of transformers allowed us to take actually a fairly complex problem of global tracking that has usually been done with fancy optimizations and just sort of quickly replace all of this with a few layers of cross-attention. And then we just use data sets and sort of deep learning to figure out the problem of global tracking. It's also super fast. So we train these trackers together with the underlying detector, and the tracker itself runs in less than 1% of the time of the detector. So even though sort of cross-attention and self-attention are fairly costly operations, in tracking, this is nothing compared to what the underlying object detector does. Excuse me. All right. So this sort of concludes the awesomeness of transformers part of the talk, and I'll just briefly highlight some other stuff that we have here at the conference. Just if you're interested, and you can go check it out. They also put up when and where you can see these papers. The first one is actually on speeding up transformers. As I mentioned before, in tracking, transformers are not a bottleneck. In video recognition, if you look at sort of the fanciest video recognition models out there, transformers can become a bottleneck. And the issue here really is that in video recognition, the transformer computation sort of scales quadratically, or self-attention operation scale quadratically with the length of the video. You can cut this down a little bit by using cross-attention, again, using queries and cross-attention to summarize the video, but it's still still quite memory intensive. Now we're able to show at a paper that's going to be presented on Thursday is that you can cut this down to sort of a constant runtime per frame. So you can amortize a lot of the transformer computation if you choose the right kernel. So instead of using sort of a softmax attention kernel, if you use a box kernel or Laplace kernel in time, you can still use softmax across spatial features. But if you use a box or Laplace kernel in time, you can cut down the time dependence of the transformer to something that's constant per each time step. So you can run a video model that gets you an output at every single time point in time, but you only pay a constant time cost for it. And it works quite well in practice. We have sort of two versions of our model. We have a fast one, and then we have the regular one. The regular one works is quite a bit better in both detection and anticipation on the TUMOS 14 data set. And then the fast one is roughly at the state of the art, but it is sort of real time. And it's one of the first models that can sort of do video recognition in real time. You can see this in the poster session on Thursday. It's going to be poster 9. Then the other thing that my lab is actually actively working on is trying to scale up recognition. And to give you sort of a flavor of what we're working on is, sort of if you run a standard object detector on this sort of messy scene of sort of, okay, a little mildly messy scene here, you can see you can find some of the objects, but you can find them with a fairly high confidence. You can even find this sort of monitor here in the back that's occluded with a very high confidence. And segmentation looks quite well, looks quite good. Now the main issue is that we actually could detect a lot more objects in here. So we could detect all of this sort of these papers here. We could select, we could probably detect a tissue box. The detector would be capable of doing this, but the detector does not know how to name these objects. All right, and so the what we did in a paper that's going to be presented, I think, also on Thursday, is we showed how you can train a detector using all of the awesome supervision that you get from ImageNet. And so you can get a detector that trains on 21K classes. And this is the result. So now you have a detector that can detect almost everything in a scene. It also works quite well if you go if we made this public, people on the internet started using this, and it works quite well on sort of random pictures that people have taken. And again, it's on Thursday, poster 22. Now, the final thing I would like to mention is that whenever you train with lots and lots of object categories and classes, you have to deal with a long tail. And so in a paper that's going to be presented on Tuesday, we'll show how you can actually do long tail detection in sort of a principled manner. Long tail classification has a lot of interesting math and theory behind it on how we can sort of learn detectors that deal with the long tail of object classifiers that deal with the long tail of object classes, but for detections, this doesn't exist. And so what we're able to show here is how we can reduce sort of object detection, MAP, in the long tail. How can we reduce this to pairwise ranking in the long tail, which then has a connection to classification? So we can pull in all the long tail classification theory into object detection by just connecting MAP and detection error to pairwise ranking and then classification. Sorry, was there a question to this? I heard some. Okay. Yeah, this works very well. It gives you sort of a 1-point boost on Elvis throughout many different experimental settings. It works well across different classifiers. It works well across sort of different experimental setups. Yeah, and with that, I'm happy to take any questions.
Yes, thank you very much for the very inspiring discussion. Are there any questions from the audience?
How did you do it? How you did the SLAM? So the mapping is continuously moving.
Yes. Okay, great. This is a great question. Okay. So let me see if I can find the slide again. Sorry. So the way we did the SLAM in the mapping is we just used, so the benchmark itself actually provides you with a camera pose. So we go back here. So the benchmark itself, for each of the set of images, it comes with a pose. And that pose was actually estimated. I think they even used LiDAR to estimate this. We didn't actually have to run SLAM to do well on this. So this, the camera pose, or the estimate of the camera pose, comes together with the images. And this is something I forgot to mention. And thank you for pointing this out. So it's not just the images we get here. We do get sort of camera intrinsic and extrinsics. For the intrinsics, this is the calibration. For the extrinsics, this is actually run, I think they use GPS and a bunch of other things to infer the camera pose.
All right, thank you. Are there any other questions from the audience? If not, I would have a question also regarding the first work. Since you're like heavily improving in terms of speed, in terms of the method, you're not beating the state of the art in that method. Can you maybe elaborate what is kind of missing to close the gap to state of the art?
Yes. I think the short answer is data. I think we don't have enough data, especially in the sort of, we do very well close up. So we are able to, let me clear this real quick. So we're able to do very well sort of in areas that are close to the camera. So let's say this is the vehicle here. We do very well here, but we don't do very well in areas further out. And that's just because I don't think we have enough data and there is too much variability this far out to learn the geometric transformation well. And so my bet is if we just had sort of 2-3 times more data, the transformer would be able to learn to do geometric reasoning well out further out. There might also be data augmentation that we could employ that we haven't employed yet. There might be some other tricks, but mainly it's the data that we don't learn the geometric transform very well for points that are far away.
All right, thanks a lot. That makes a lot of sense. Are there any other questions from the audience? I think currently no. So, oh, there's one question.
Hi. Yeah, so I had a question about the tracking part, and so you kind of have a sliding window which you go through a video in order to find like tracks of objects. So how dependent are you on kind of like that the track is similar enough to itself? Did you try kind of like skipping 10 frames for every frame so that you would get longer tracks in that sense, or does it scale in that way?
Yeah. Yes. So if you had a smaller overlap between consecutive frames you run this on, the association will actually get harder, and we might not get away by just looking at overlap. We might have to look at some of the features. The nice thing of going frame by frame is that things really don't change very much. In this global tracker, if you go frame by frame, things don't change much, and hence you can just do this greedy association. We haven't tried going sort of 10 frames further. We've tried sort of skipping more than one, and it actually doesn't change much in the sense that like you don't actually gain anything by skipping frames. The transformer on top is super fast, and so running it at every single frame doesn't actually change. Sort of rerunning it at every single frame doesn't change. What really matters is how often you run the detector that's sort of running that feeds you the boxes. And that's the resolution at which sort of the speed considerations matter. The shift in the windows that we consider is less of an issue. Does this make sense?
Okay, thanks a lot. Are there any other questions from the audience? As far as I can see, no. So with that, I would like to thank you again for the very inspiring talk. It was very great having you here. And please join me in thanks to speaker again.
Thanks for having me.
Okay, then thanks for joining virtually.